Hello, so today we are going to look at QuickSort. It's a sorting algorithm. There are many sorting algorithms, but today we are just going to focus on QuickSort and explain it. So QuickSort is a type of sorting that uses divide and conquer paradigm, and it's as in terms of complexity, it has a worst case running time of O(n squared. But often it's the best practical choice because it's very efficient on the average case. So in the average case and the best case scenarios, its running time is O(n log n). Additionally, the constant factors involved in this O(n log n complexity are very small, and so it kind of beats other sorting algorithms that have still O(n log n complexity, but are still in terms of constant factors are bigger than QuickSort. So QuickSort involves two things: the partitioning steps and then the dividing step. With the partition step, there is something that is very important, which is the pivot. And the pivot can be chosen in different ways, and that's where there are different implementation of QuickSort. And so the pivot can be chosen as, for example, the last element. It can be the first element. It can also be chosen as the middle element, or even more sophisticated ways of choosing it, like the median of medians, or the example that I have here, which is taking the two leftmost distinct values and picking the largest one. So taking the two leftmost distinct values of the array that we want to partition and taking the largest one. And so let's first just look at this example here where we choose the pivot to be the last element. So what do we do? First, the partition step, which you can see here, where 3 is our pivot, and so we take all the elements in the array that are less than 3 and we put them in this portion here, and then we take all those that are bigger than 3 and put them in the right portion. And so this is the partition step. Then after that, we recurse on each subarray, and then we sort that one using QuickSort also. And so you can see here, we pick the pivot again as the rightmost element, and then we take all the elements less than it and put them to the left, and all those bigger than it, we put them to the right, and then we recurse again and do the same thing on the right side. And at the end, once we've done all of this, the last step would be, which is the conquer step. So since I said it's a divide and conquer type of algorithm, and so the divide step is this partitioning step, the conquer step is this recursing on the subarrays, and then the combine step in the divide and conquer algorithm is here. In this case, there is nothing needed to do because they are sorted as a final result, so we can just use that basically, because right now you can see -6, -3, 1, 2, 5, 6, 8, 9, that's sorted. Just by doing this partitioning step and putting things on the left and things on the right that are smaller and bigger, we end up with the sorted list by default. So this is the case when picking the rightmost element as the pivot. If we pick, let's say, the two leftmost distinct values, so selecting the pivot, so there is a step. So there is the partition step, but there is also selecting the pivot. Here in this case, it was really simple. Selecting the pivot, we're just picking the rightmost element. But let's say in this case, we take the two leftmost distinct values and just pick the largest. So this is our select pivot routine here. We will take the larger of the two leftmost distinct values. Other implementations can take the median, for example, or the median of medians. And so here you can see, doing this one, the two leftmost distinct values, that's 3 and 1, and picking the largest one, that's 3, right? And so we partition using v equal to 3, and then we take all the elements less than 3, we put them on the left, all those bigger than 3, we put them on the right, and so here 2, 1, 1 are less than 3, and all the rest is bigger or equal to 3. So that's the partition step. And again, we'll curse on each subarray, and then we take the partition of that. So 2, 1, 1, the two leftmost distinct values are 2 and 1, and the larger one is 2. So pick that as the pivot. And so you can see here, since you can see here we have all those less than 2 on the left and all those bigger or equal to 2 on the right. Same thing here with partition by v equal to 5, and you get the idea. We keep doing this, and then at the end, once we are done basically when there is no two leftmost distinct values here. We can't select any pivot. That's when we are done. So you can see for 1, 1, we can't select any more pivot, and so we are done. For 2, we are done. 3, 3, we are done. And that way we have the leaves in this, if you consider it a tree, that our sorted array. So those are the couple of examples. We can choose the pivot as the first element, and we'll end up also with a sorted array. And now let's look at the algorithm. So the algorithm of QuickSort, we call QuickSort on the entire array. So I have here the implementation on the left, and an example on the right. So first we call QuickSort on the array from 0 to n-1. And QuickSort routine takes the boundaries, left and the right sides. So you can see here for this, every time we recurse, we do it in place. So we are not passing a new array, we're just passing the same array, but with the boundaries that we need to operate on, since they are smaller, right? And so here, so we keep doing this until the left and right pointers cross, because at that point, that means we sorted the entire array and we don't need to do anything anymore. And so we start out with the entire array to sort the entire array, and then we, as long as left and right haven't crossed yet, we partition the array. So that's the step where we pick the pivot, and then we put those less than the pivot on the left and those bigger than the pivot on the right. And so here we have the original array 6, 5, 3, 1, 4, 2, 7. We call QuickSort from 0, which is the position of 6, to n-1, which is the position of 7. And so you can see here our left pointer was on this one, and right pointers was on this one. And so we partition. We pick a pivot to partition on. So let's say we pick 3. Then we need to recursively sort from left to the pivot -1, and so that's 1 and 2. And then so we recursively sort that smaller subarray, and then we pick the other subarray, which is from the pivot index +1 to the right, which is this portion from 6 to 7, and we sort on that. So this is the divide. This is the concur step, and this partition here is the divide step, and then the combine step is just by default, since we ended up sorting everything, so we don't need to do any combine code, anything in the combine portion of the algorithm. And now, so that's the layout of QuickSort, but the partition step subroutine is important. It's the rest is easy. The partition step is the most important one to understand here. And so the partition also takes left and right, and basically just takes the element less than the pivot, put them on the left, and those are bigger than the pivot, it puts them on the right. So the first thing we have, select pivot in the array. So this routine is where implementation differs. So some implementation choose the first element, some implementations choose the right element, some implementations choose the middle, some implementations choose, as I said, like in my example here. And so here in our generic algorithm, we're just saying select the pivot. And so let's say in my example here, I select the pivot as 3. So the first thing we need to do is swap the index. So P is just the index of the pivot. So I swap that with the right element. And so I take 3 and I swap it with the right element. Basically, the essence of the partition step is just select the pivot and then put it on the right side, rightmost side, and then look at the entire array from the left pointer until the right pointer -1. And basically, if you encounter an element that is bigger than the pivot, leave it as it is. If you encounter an element that is less than the pivot, put it on the left. And so we have a pointer that keeps track of the left, where we put on the left the smallest, the last element smaller than the pivot. And so that's this store here. And then keep doing that. As soon as you find an element that is less than the pivot, put it at the store position, so that at the end we end up with all of those smaller than the pivot on the left. And then the last step would be to put the pivot element at the end of all those smaller than it. That's the essence of this. And so here, once we put the pivot to the far right, which is 3 here, we put it to the right. We initialize a store, which is just an index to keep track of where we put the last element less than the pivot. And so now we start traversing from left to right -1, which is just the element right before where we put the pivot. And so if we find the element that is less than the right element, which is our pivot basically, then we swap it with where we have store. And remember, store is just where we last put the element less than the pivot +1. It's basically where we should put the pivot, and it starts out at the left. So first we find 6. We are at 6. And so we initialize our store to 6 there. And then we keep traversing with our I from left to right -1. So we go to 5. 5 is bigger than 3, which is the pivot, and so we continue. 7 is bigger than 3, we continue. 1 is less than 3, and so we have our condition here. And so we swap 1 with the store element. And so we put 1 here, and we advance our store position at 2 here. And we keep going. So 2 so we keep going. So 5, so our I here is at 6. And so we check 4. 4 is bigger than 3, so we continue. 2 is less than 3, and so our condition here is valid, and so we swap AI with A store. So we swap 2 with A store, which is 5. So we swap 2 with 5. And then now I reaches the end of the for loop iteration, and we are done. And you can see as a result we are done with the for loop, and then at the end we swap the store position with the element on the far right, which is the pivot. And so we put the pivot at the end of all those smaller than it, so that it can kind of divide those smaller than it and those bigger than it. So you can see here we have all those smaller than 3 are on the left, which are 1 and 2, and all those bigger are on the right. So why is that? Because anything bigger than the pivot, we left it in its position, we didn't touch it by using this if check. And anything less than the pivot, we put it on the left. And then at the end, we put the pivot just next to all those smaller than it. And so by doing that, we kind of put it in the boundary between those smaller than the pivot and those bigger than the pivot. And that's pretty much what we are doing here. I think it will be basically with this quick sort, once we understand the partition step, there is nothing else to do. So I'm going to just show an example with this array using a visualization here tool. Okay, so let's take this, let's create this array. Let's choose QuickSort, and let's pass this array. And so you can see our array here is not sorted, so let's run this QuickSort on it. Let's use a slow. So you can see here we have our algorithm here that works first on the entire list from 0 to 8. And so we select the first element as the pivot, so that's a valid pivot selection heuristic. We can choose the first element, the last element, whichever one we want to implement. And so this visualization here uses the first element. And so what do? We check the element. So we start. So you can see some algorithm implementation first swap the pivot with the right position. Some implementation don't. Both are fine, and so this one doesn't, but that's fine. But the interesting part is going from the left to the far right and checking if it's less than the pivot, put it on the left side. If not, keep it as it is. And so 12 is bigger than the pivot, so we don't touch it, we leave it as it is. So you can see it was kept where it was. 4 is less than the pivot, so we should put it on its left. So put it on the left. And then we advance. 3 is less than the pivot 5, so put it on the left. Same thing, 2 is less, so put it on the left. And then 11 is bigger, so we leave it as it is. 9 is bigger, so we leave it also as it is. 10 is bigger, we leave it as it is. 1 is less, so we put it to the left. And notice every time we don't put it to the far left, we just put it after the last element smaller than the pivot that we handled. And so we put it after 2 here. And the last step is to put the pivot at the end of all those smaller than it that we already handled. And so the smaller than the pivot that we last handled, that was 1. And so we put the pivot right after 1. So we put 5 right after 1. And now you can see we have all those that are, so that's the last step of our algorithm here. Swapping the pivot with the last position of those smaller than it. So you can see now we partitioned the array into all those smaller than 5 to the left, all those smaller than, bigger than 5 to the right. So anything bigger than the pivot, we keep it as it is, and anything less than the pivot, we put it on the left. And we keep track of where we last stop it at the left side. And so that was just the first partition, right? Now we need to address the we need to do this the divide step, and so we need to handle the left side. And so you can see here we chose 1 for the left side as the pivot, and so 4 is bigger than it, we'll leave it as it is. 3 bigger than it, we'll leave it as it is. 2 bigger than it, we'll leave it as it is. And 5 is, we are just handling, you know, from 1 to 2. And so now we choose the right side, 4 to 2, and we sort that too. And so you get the idea. Basically, we partition, we divide, we sort the left side and then we sort the right side, and the combined step is automatic. Let's just make this fast. So you can see it. We will end up by just doing this. You can see we'll end up with the sorted list, and that's pretty much it. And so I have here an implementation of it. We saw the algorithm in pseudocode. Now let's see a Python implementation. So in my Python implementation here, the selecting the pivot routine is just choosing the rightmost element. And so you can see here, we can change this one to be a left plus right divided by 2 to pick the middle element. It can be the one that I did here, picking the larger of the two leftmost distinct element. But the essential idea is in the partition step, we select the pivot to give us the value of the pivot. In my implementation here, I'm doing the swap between basically putting the pivot to the far right, and then I select the store position, which is the left side here, and I go from left to right, which is this here, right -1, so that I can process everything before the pivot to put it in the right position, basically. And then I check if it's less. Anytime I encounter an element less than the pivot, I swap it with the store position, which is what we are doing here. And I advance the store so that I handle the next place that I found that is less than the pivot. And once I do all of that, you can see here, if it's bigger than the pivot, I don't touch it. I leave it as it is. But if it's less, I put it on the left side. And the left side basically here is represented by this store index. And at the end, once I'm done, I know that all those less than the pivot are before the index of store, and all those bigger than the pivot are after the index of store. So I put my pivot element in between these two, and that's doing this swap between a store and a right, right? A right is just the pivot, remember? Because we put the pivot at the far right. And then, so that's the partition step, and that's the select pivot subroutine. So we have our subroutine that we need for QuickSort. And so in our QuickSort implementation, we just partition the array to get the pivot position. And then, so you can see here I'm returning star, which is the pivot position, because I swapped right with star. So I know now that my pivot is in the star position. So I return that as p here. And my quicksort just recurs on the left side, which is from left to p minus 1, and on the right side from p plus 1 to the right, which is basically what you can see being done here. And then the pivot gets left here, and then we recurse. And so we recurse, and this gets called again, and then the partition gets called again until we have only one element and we are done, right? And we call quicksort on the entire array to get the entire array sorted. And that's the Python implementation of this. So you can see it's very much just a translation of the pseudocode that we have here. I think it's useful to see quicksort in Haskell, even if you don't know Haskell. It just helps in seeing it in a clear way. Because Haskell is very good at showing algorithms to their essence. So you can see here in my case, I'm just calling quicksort on an array where this is x is the first element and the rest is this xs. So I'm choosing my pivot as the first element, and so I just take the smaller portion that is smaller than the pivot, I put it on the left, I put the pivot, and then I put the values bigger than the pivot on the right. That's pretty much all we are doing. And what is the smaller portion? The smaller is all the element of the array after the pivot, which is the first element, that are less than or equal to the pivot, and the bigger element are all those in the array that are bigger than the pivot. And so I just I concatenate them, and that's pretty much it. So you can see here it's just, in my case here, I'm picking the first element as the pivot, put the smaller one than the pivot to the left, the bigger ones than the pivot to the right, and then what is the smaller portion? It's all elements less than the pivot and all the elements bigger than the pivot. And using this, we just keep recursing until we are done. So that's all there is to it. Now let's just look a little bit at the time complexity. So we said earlier that the worst case O of n squared for quicksort. So I just want to touch on that a little bit. So quicksort usually works by taking a pivot and then putting all the elements lower than the pivot on one side, and all those higher on the right side. That's what we did earlier, right? So it recursively sorts the two subgroups that we just divided on using what we did here, right? Now, why is it sometimes O of n squared? So it can be O of n squared if at each time we pick always the worst pivot. What does the worst pivot mean? If we have if we always pick the highest value element or the lowest value element, and especially in a list that is, or in an array that is nearly sorted or sorted already, then that means that in our partition step, since we always pick the bigger element, let's say as the pivot, we will partition into just all those less than the pivot would be the entire array that we are recursing on. So at each step we will divide by only one, right? So at each position we'll divide by only one, and so that means that at each step we'll go from n to n minus 1 to n minus 2 to n minus 3, because all those, since it's the highest element, then all those less than it are the entire n minus 1 portion of the array, right? And so since we do n and then divide on n minus 1, n minus 2, n minus 3, so it's no longer dividing by 2 at each step. It's just reducing by 1 at each step. And so that means that we iterate, that means that we do n groups, right? And each time we iterate n using O of n to do the partition, right? And so that ends up to be n by n, so O of n squared, right? So that's when the worst case can occur, is especially when the list is nearly sorted and we pick, let's say, the highest element, then we have only n minus 1 as a subproblem, and then after that we have n-2 as a subproblem, and then n-3 as a subproblem, so it ends up being O(n squared, and so that's where it's worst case. And the best case is just when we almost divide by 2 each time, and so we end up doing log of n because we divide each time by 2, and so we end up doing, for the partition step, we are doing O of n, and since we are dividing by 2 each time, we are doing O of log n, and so O of n multiplied by log n. That's the best case. And yeah, so that's pretty much it for QuickSort. I hope this was useful. See you next time. Bye.